Okay, so 15D is this weird diversion, and they talk about complex roots of polynomials. And you learned that complex numbers come in conjugates. So if like 2 plus 3i is a conjugate, then 2 is a root, then 2 minus 3i is a root. But then they throw this, they say, well, what if what happens if x equals, 7 and 2i are the roots of a quadratic? And so you work backwards. You say, well, that can't be true, but the book is saying you can. So you work backwards. You say x minus 7 equals 0, and x minus 2i equals 0. You multiply them together. And you do FOIL, and you want to see, minus, 2i plus 7x, and then plus 14i equals 0. And so this is a polynomial whose roots are 7 and 2i. Those are the roots of that polynomial. And so we need to just define something. A real what we study in this class are real polynomials. And real polynomials are polynomials whose coefficients are real. And so we see here, if you have a polynomial with complex coefficients, you don't need conjugates. Once again, what you learned in 10th grade. So once again, if your coefficients are complex, 2i can stand alone. We're not interested in this class. We're not interested in that. So the idea is, here, complex roots come in pairs, come in conjugate pairs. And so they say let z equal, a plus bi. Z is x plus iy, and they say if f of z equals 0, then its conjugate, the book uses the Saria, equals 0. If z is a root, then the conjugate is a root. Fine. Then they're like, oh, you should memorize this formula. So if you have like a complex number as root, you can quickly get the polynomial. And so they go through this thing that I was never a big fan of, really, and I kind of worked it out, and I was like, okay, that's kind of interesting. They say, in the way that I work backwards here, sorry, let me move this over. In the way that I move backwards here, they say, fine, x minus, let's call this a plus bi. So x minus a plus bi, and then the other root is a minus bi. So like I did there and worked backwards, if the roots of the quadratic are a plus bi and its conjugate, we can work backwards, and that's equal to 0, right? And we can do the FOIL method, so we have x squared minus, x times a minus bi minus x times a plus bi. And then we have plus a number times its conjugate. So once again, I'm just working backwards, right? And so we work this through. We work this through, so we have x squared. I have minus xa plus xbi minus xa minus xbi. And then we know from our study of the previous unit, this is equal to a squared plus b squared. Well, we notice that this goes out with this, and the book comes up with this really interesting formula. It says the quadratic whose complex roots a plus bi and its conjugate is x squared. They can say minus 2xa 2ax plus a squared plus b squared. I'm going to leave off the 0. Well, what is this? This is x squared. A is the real part, right? You know, the real part of z is a. So they write minus 2 times the real part of z, x, plus, what's this? It's the modulus squared. And then the unit asks you to go through this exercise. And this is how the unit is. I'm not a big fan of this, so I'm going to teach you something a little bit faster. The other thing they throw in there, so for example, let's say the roots are, 3 plus 2i and 3 minus 2i. And they say, where did this quadratic come from? And you would say, okay, well, the real part of z is 3, right? And the modulus of z is radical 13. So radical z, the modulus of z squared is 13. And so we get the quadratic x squared minus 6x plus 13. If that equals 0, and we solved it, it would generate these two roots. Okay, that's 15D. And then the last thing they say in 15D is, and they're kind of throwing this stuff out there. It's a weird chapter. Usually I'd skip over it. The last thing they would say is, just the fundamental theorem of algebra, which I don't know why it's in here, but it's here. Basically, a polynomial of degree n has n roots, some of which might repeat. Okay, that's 15D. Let's move on to 15E, something a little faster. So 15E is simply, did I put that in there? There we go. And let me move over here. Let me move all the way up to 4th, sorry. Okay. Well, 15E it's the sum and the product of the roots. And the idea here is that by looking, if I give you the roots, you can quickly create the polynomial, the quadratic or the polynomial. Specifically, we're going to be looking at quadratics and a cute little trick for cubics, and we're going to be looking at the sum and the product roots of all polynomials. Okay, let's start with the quadratic. Simply put, I'm going to erase this. Let's start, so sum, this is 15E, sum and product of roots. So let's start with the quadratic, and the idea is you have two roots. Let's call them P and Q. So let's work backwards. So we say x minus P times x minus Q equals 0, right? So we have x squared, you're doing the FOIL method, minus P plus Q, x, plus P cubed equals 0. Now, we know quadratic is ax squared plus bx plus c. So let me throw in an a. Let me multiply everything by a. So we have a. And if we match it up to original quadratic, we get kind of something interesting. Once again, if we match it up to ax squared plus bx plus c, we get some interesting connections. It turns out that, well, A is A. It turns out that that negative AB plus Q equals B, so therefore the sum of the roots is negative B over A, and if we match up APQ to C, it turns out the product of the roots is C over A. Sorry. So the product is C over A, and the sum of the roots is negative B over A. Actually, you know what? Yeah, this is the sum. This is the product. You know, let me take it with the cubic, because in the chapter they show you this cute little thing for cubics. So let's look at that. Let's look at the cubic. The cubic has roots P, Q, and R, right? So we have x minus P, x minus Q, and x minus R. So that's equal to 0. And so we have, what do we have here? So we have, I'm going to do these first. So we have x squared minus P plus Q, x plus PQ, and I'm going to multiply that by x minus R. And then I'm going to do like a major, like bear clause, like major, like FOIL. And so we have x squared times x, which is x cubed. We have x squared minus r x squared. We have negative P plus Q, x squared, plus r times P plus Q, x. So that was this, this. And then the last one is PQX, right? PQX, right? And then minus PQR. Okay. Let's get this cleaned up. Well, we don't need to get it cleaned up. We have what we want. Once again, I put these underneath. So with this, we're going to match this equation up to, oh, I'm sorry, and the last thing we want to do, I apologize, is multiply everything by A. So we're going to A. Okay. So if we match this up to AX cubed plus BX squared plus CX plus D, right? We see that A is A. We see that this is kind of cool. We have negative A times R plus P plus Q is equal to B, and therefore the sum of the roots, once again, is B over A. That's kind of cool. It's not a coincidence. That works out for everything, every single polynomial, real polynomial, the sum of the roots is always negative B. And notice once again, B is the next term down. Let's look at the product here before I get to this cute little thing that they kind of think is funny. But right here we have negative APQR equals D. So PQR equals negative D over A. So in both cases, we're looking at the ratio of the constant over the first term. The constant over the first term. If your polynomial has an order of like 2, 4, 6, 8, it's going to be positive constant over first term. So if the polynomial has a degree that's even, then the product is equal to the constant over the first coefficient, lead coefficient. That's what we talked about that. For polynomials with order that's odd, to the third power, to the fifth power, to the seventh power, the product, once again, is equal to negative the constant over the lead coefficient. Okay. And so, good. Good. Talked about that. Good. Good. Perfect. Let me just talk about this weird C term in the cubic. It's not showing up anywhere else, but it's kind of cool. It turns out that, and I'm sure it showed up on an IB one time, and so the book put it in there. You never know if it's going to show up. Let's take a look at that C term for the cubic. Remember, it's the coefficient in front of the x. Well, what's going on here? It turns out that PQ plus PR plus RQ is equal to C over A. It's a nifty little trick. It's there. It might show up. Probably not. There's one or two exercises in the book. It can't hurt to know. It's fun competition stuff. But I'm not going to ask you anything right now. Let's just do some questions. How are we doing for time? Perfect. Yeah, this is cute, right? Okay. Let's try some problem. The roots. So let's do some examples. The roots are 5 and -2. How do you find the quadratic? So you say, okay, the sum of the roots is 3. The sum of the roots is 3, so that's -b over a. The product of the roots is -10, and that's c over a. If we let a equal 1, now think about this. With your quadratic, if you have nice integers, that a is always positive. You remember from quadratics, the fractions start to show up when that a was 2, 3, 5. So if we let a equal 1, that means b equals -3, and c equals -10, and therefore the roots of 5 and -2 come from the quadratic of x squared minus 3x minus 10. Let's try another one. The roots are 1/2 and 7/3. The roots are 1/2 and 7/3. Okay, so we go through this again. What's the sum of the roots? In this case, you should know how to do this quickly by hand. 3, 14, 17 over 6. So that's -b over a. The product is 7 over 6, and that's c over a. So therefore, we're going to let a equal 6. We're going to let b equal -17. And we're going to let c be 7. Therefore, the quadratic from whence those roots came is 6x squared minus 17x plus 7. Let's try another one, and then let's look at that last book problem. So, how about a 2 plus 3i? Let's look at, perfect. So the problem we did, 2 plus 3i, and then we used the book rule, but I'm not a big fan of the book rule. I like this better. So let's see. The roots are 2 plus 3i. So if I tell you in a real polynomial, one of the roots is 2 plus 3i, you know immediately the other root is 2 plus 3i. They might say it's a cubic, but I like just creating the quadratic. So if 2 plus 3i is a root, then 2 minus 3i is a root. Let's get a quadratic out of this. So we know that the sum easily is 4. And we know the product easily is 13. Right? Because it's 2 squared plus 3 squared. We know that this is -b over a. We know that this is c over a. We know that a equals 1 because there's no fractions. We know that b is -4, and we know that c is 13. So this came from x squared minus 4x plus 13. It's a quadratic. It's a real polynomial. We know from we know that 16 minus 52. We know the roots are going to be complex. Nice. Now let's look at the book problem, that original book problem, and they basically were like, let's see, they said, this is work problem 1514. They said, given that 1 minus I radical 6 is a root of f of x, which equals x cubed plus x squared plus x plus 21, find the remaining roots. So, how I would do it? Well, if it's a real polynomial, I'm given this root, I'd say, okay, first, let me create the quadratic. For 1 plus or minus I radical 6. Okay, so what's the sum? Well, the sum is 2. That's easy. What's the product? Well, that's not difficult either. The product, I know, is 1 squared plus radical 6 squared, which is 7. So I know that this is negative b over a, and I know that this is c over a. So I know my quadratic, which is part of that, is x squared minus 2x plus 7. Well, what's the next step? I have the quadratic. What times this will get me to that? Well, what you're going to see is the 7 times 3 will get me to 21. That's your answer. And that's the tricks of the trade. So I'd like you just to really know how to do this product of the root, sum of the roots, try the cubics. Remember the rule. They love the stuff about, it's like to the 8th power. What's the sum of the roots? What's the product of the roots? And you just have to know whether it's even, it's c over a, constant over lead. And if it's an odd polynomial, if the order is odd, you have to know it's negative constant over the lead. And that's it.